I know we've done some videos lately on Threadripper builds and DDR5 and the DDR5 throttling problem, but it's more common than I realized. I also got a lot of questions from software folks in our community that, you know, they're not following every single video and they didn't really understand the hardware aspect nuance. So I'm doing this video as a kind of chat explainer, a little more low level, because we've got to keep our DDR5 stable and safe because, well, we can't afford to buy more. It's true, DDR5 might be the reason that you're experiencing mysterious system instability. The problem is the memory? Yeah, the problem is the memory. That's true in desktops as well as workstations. I think it's flown a little bit under the radar as a source of instability for far too long, but there are a lot of threads on our user community and our forum where the instability is resolved by just adding a little bit more airflow over the DDR5. And now I've found a catastrophic bug where your DDR5 memory will overheat itself past the safe limits, past the safety cutoff that's meant to throttle or shut the system down. I've been meaning to make this video about DDR5 for a while based on what I've learned from the community over the last year, but the urgency is now up to 11 because the RAM prices are insane, first of all, and because I discovered ASUS Threadripper motherboards aren't throttling properly at all. On the forum, we've seen systems that look haunted, random crashes, weird instability, WHEA errors, sometimes, but not always, it can be disabled, Linux RAS daemon in the logs for the Linux users. The problem disappears when the users add a little bit more airflow over their DDR5. Before we talk about the bug, I want to talk about DDR5, the thermal protection, what the throttling mechanism is and how that works. It's a whole new mechanism on DDR5, and it's not well understood, at least based on the questions that I'm getting. So let's go with this. If you paid attention to memory, maybe back in the DDR3 days, DDR5 is not DDR3 or 4, but faster. DDR5 was designed server first. Just about all memory nowadays is designed server first in a server context. That's the JEDEC standard. The JEDEC DDR5 standard was finalized more or less around 2020. JEDEC's DDR5 spec focused on higher density, better reliability, massive bandwidth scaling, which we are just now starting to see at the end of 2025 and 2026, platform manageability, and managing errors. DDR5 DIMMs are no longer just memory chips on a PCB. It now includes an SPD hub instead of a dumb EEPROM, support for faster sideband management, I3C instead of legacy I2, more design considerations for monitoring and telemetry, in other words, tighter integration with the platform firmware. I mean, there's really insane technical features in DDR5 like post-package repair, where there's spare rows in the memory chip that can be reallocated for chip health monitoring and more. Now, desktop DDR5 inherits some of this architecture, but not all of it. It's not the same team doing the desktop DDR5 design. It's not the same rigor or safeguards in desktop DDR5 as you have in registered DIMMs for workstations and servers. It's a data center product that's, trickling down to desktop. And with apologies to the desktop engineers, the server engineers are up there on Mount Olympus working hard, and then it's passed down to another team. And that other team's job is to try to remove as much as possible without making it dramatically worse. The server team's priority is not affordability, and the desktop team is also cobbling together features cherry-picked maybe from future JEDEC specifications for more speed or overclocking or voltage, and it kind of turns into a mess. See also desktop DDR5 teething issues if you were following along there. Now you know why. But for this video, I want your takeaway to be the understanding that desktop use cases are barely a blip in the design considerations for the team that's working on server class and the JEDEC standard. That's part of the story of how we got here. If we take a closer look at our G.Skill 64 gig registered DIMM that I recently reviewed here, DDR5 is still a 64-bit interface. DDR has been a 64-bit interface since time immemorial, basically. And DDR5 still presents as a 64-bit interface to the CPU, but internally it's actually split into two independent 32-bit subchannels. Why does that matter for this video? Well, better efficiency on a smaller memory transaction, less wasted bandwidth, a higher effective throughput at scale. It's easier to route the traces on a PCB. There's other reasons. But DDR5 also increases the bank count, bank groups, refresh flexibility, and all of that enables higher speeds, but it also increases the background activity inside the actual memory chips, things like refresh flexibility. See, DRAM loses its contents, the electrons like to leak out. Part of the mechanism here is that the system reads the contents of memory and then writes them back to refresh the contents. That's not new in DDR5, but that's part of the timing for that had been very strict, but DDR5's rules have sort of given you some flexibility and things have improved. Of course, that means the chips are driven harder, and more activity means more heat and more power dissipation, 15 watts per DIMM upwards of. It's important to understand that the memory on this DIMM is physically arranged in the left and right into those two channels. The halves are our two 32-bit channels, and they can more or less operate independently. And in the middle, we have our power management IC, the PMIC, and a registered clock driver, our RCD, that's here on the front. The part in the middle is the part in the middle because it's moving the voltage regulation onto the DIMM itself. The power management IC takes an input rail and locally generates the voltages that the DIMM needs to operate, VDD, VDDQ, and VDDP. Voltage regulation can be a source of interference, like radio interference, interfering with the digital integrity of the signal. Pushing voltage regulation onto the DIMM from the motherboard allows the designer to address that in their design. So the voltage regulation being closer to the memory also improves the response time when the memory goes from sleep to wake. There's a little bit of latency in terms of the power system delivering that. So power gating the DIMM when it doesn't use power, it's a key part of the thermal management strategy as well. But this has downsides. The biggest one is that this is a significant source of heat that is located right next to the memory chips, and high density DRAM chips, down here, and this little thing getting super hot up here. It's located here for hoping for the best airflow. So the reason the DDR5 gets hot is not mysterious. It's a direct consequence of the design. I mean, look, the power part is literally at the tippy top of the DIMM. The designer hopes that this will have the best shot at airflow because this is the part that gets the hottest. Some heat spreader designs actually exclude this area of the DIMM altogether because that is the hottest part of the DIMM, and you don't want the heat from there contributing to the heat from the memory because that's where the instability creeps in. There's also a source of carnage. Some of our users on the forum have pushed down too hard on the top of the DIMM and the components were too close to the edge and broke them off. And if I could segue for just a minute to talk about the ECC aspects of this, DDR5 introduced the idea of on-die ECC, and marketing has done damage with that. ECC is error correction. When errors happen, and they will happen, this is a mechanism to correct them at a low level. And on-die ECC and like ECC traditionally mean different things. Understand that DDR5 has on-die ECC, which is present in almost all desktop DDR5 memory and all registered DDR5 memory for servers and workstations like this one. This corrects certain types of errors inside the DRAM chips themselves. It enables higher density and better yields. It's almost never visible to the CPU though. It is not system ECC or traditional ECC. Traditional ECC DIMMs added extra data bits. Historically, that's an extra X8 device per rank, so the memory controller can detect and correct errors across the entire data path. It's storing and retrieving more data from the memory controller and the CPU to the DIMM. So when people say DDR5 has ECC, what they often mean is the on-die ECC, which does not protect you from signal integrity issues and most types of thermal instability, platform firmware bugs, as we're going to have to talk about with ASUS, that type of thing. Modern workstation platforms, Intel Xeon and AMD Threadripper, use DDR5 RDIMM ECC. Look at our DIMM here. There is an extra chip per channel. That is not on-die ECC, that's an extra chip. This is the type of traditional ECC that's visible to the system and the platform. Our workstation DIMM in this aspect is basically a server JEDEC DDR5 spec. The extra bolted on stuff is just mostly for overclocking and handling more RAM timing profiles and being able to tolerate higher voltages. DDR5 is designed with a register buffer logic and adding, there's clock control circuitry and more telemetry, and that brings up the density and power draw. That's the extra stuff on here. And again, in servers, this isn't a problem in servers because they're loud and they have extreme airflow. But our workstations are different. I mean, this one is running and you can barely hear it. If you followed our past content, you know this part already. We've been designing and 3D printing printable RAM shrouds and adapters. This one's for EPIC. All the way back to Zen 4, we've been doing this. Why? Well, because in servers, I typically see DDR5 memory operating at 50 to 60 degrees C, and I wanted to replicate that just instinctually on workstations. I don't want a workstation on my desk with screaming loud fans, but servers have screaming loud fans and engineered airflow. Workstations, you got to sort of carefully manage this kind of thing. I've also worked extensively with Dell and Lenovo Threadripper workstations. In those systems, the entire platform is slightly underclocked. Memory in those systems is always a ducted airflow situation, and the thermal behavior is predictable and controlled. Now, compare that to the many DIY boards and DIYers and many system integrators, I think, that have to deal with it. They get screwed, in my opinion. The DIY folks like us and integrators are screwed because the boards are not really designed for that. I want you to look at the change. From the TRX50 WSA or Sage A, this is the A version. Look, the top is open here. The CPU is moved up a little bit. There's not this blocking heatsink at the top. The old version of this board, your top DIMMs here are basically completely enclosed. Check out this system versus this motherboard. It's still not fabulous because the VRMs are designed, like there's little fans here in the VRM heatsinks, but they're not in any way helping the airflow over the DIMMs situation. So this board is a little better, the A version of the board is a little better than the older version of the Sage motherboard from ASUS, but this is still troubling. And that's just TRX50. On WRX90, I think it's a little bit more of a challenge depending on the board vendor. And so our 3D printable fan brackets have come in handy over the last couple of months. So bottom line, Falcon Northwest found a lot of the same kind of things that I did, which is like, well, in this configuration with heat spreaders and this application, it does actually make sense. And so their QC team reached out and I confirmed with them that, yeah, this is actually a problem on ASUS boards. Go Falcon Northwest. And that's also part of why we have the forum thread that has 3D printable options, like, you know, some of these brackets that I have here and some of them that, you know, Kelt at Falcon Northwest made out of aluminum, improving the airflow over the DIMMs. And G-Skill has also shown me that the kit of memory you have matters a lot too. You know, their challenge was, our memory doesn't need heat spreaders and it works better without it. And they are correct as long as there's airflow over the DIMMs. DDR5 DIMMs typically expose multiple temperature zones. One sensor near each end of the module, which is called for in the specs, at least the JetX specs, and one that is often on the SPD hub or where the voltage regulation area is in the middle of the DIMM, because that is a completely different thermal situation. The platform can use this information to throttle memory when either the voltage regulation part or the memory part gets too hot, and those temperatures are different. Silent throttling is not great, but it won't kill your hardware. We did a video on that back in July. In that video, I called for heat spreaders to deal with the heat issue. And I learned a lot since then, and I would have to revise my position on that since then to say that heat spreaders are not necessarily always called for. This G-Skill kit in my testing really changed my mind on that. And there's another video about that. A little bit of airflow with this kit of memory works great. It's effective without heat spreaders. But the heat spreaders make it harder to do airflow, especially if you have passive ducting. So it's this weird situation where a ducted system, like if you 3D print something like this, or you're running Lenovo or Dell, is going to work better with memory that doesn't have heat spreaders. But often a DIY system with a little bit of airflow under normal and not torture test scenarios will do better with heat spreaders. TRX50 is better than WRX90 because WRX90 packs more in. But the assumption on all of this is that throttling actually works. Throttling is a totally new feature of DDR5. It halves the memory clock in thermal constraints, or at least it's supposed to. It prevents thermal runaway from damaging the DIMMs, because these will happily get to 140 degrees C until they fail catastrophically. It does not, if it's not working, the hardware can die in those scenarios, in other words. The DIMMs specify the temperature of their zones, i.e. it is not atypical for some of the DIMMs that I tested to tolerate 115 degrees C in the voltage regulation area, and they that's not just them tolerating that, that's their spec, whereas they also say don't let the memory temperatures get above 75 degrees C. So these three regions on the same PCB having that kind of a temperature variation is perhaps a little troubling, but on the ASUS TRX50 and the WRX90 boards, at least as of December 2025, the current version of the BIOS, the throttle points specified in the DIMM SPD are not being honored almost all of the time, whereas other boards, Gigabyte and ASRock, are working fine. That means that DDR5 can exceed its safe operating temperatures. Now, at best, this is just going to lead to ECC errors and system instability. You'll see that as WHEA events on Windows. You can actually disable that in BIOS, be careful, or RAS daemon in Linux. And because this often happens under load, users can blame the CPU, maybe it's not seated correctly, maybe the GPU, maybe the power supply, or just, Linux is being weird. This is not theoretical. This is happening on the forum. I've got a lot of data now for this kind of thing. On the ASUS boards, I could get the throttling to work after hitting the clear CMOS button and then loading optimized defaults in the BIOS, but not changing anything, and then immediately testing. But then after I did a soft reboot or just reset the system, it stops mysteriously. Not even loading an Expo or XMP profile. I thought I was losing my mind because even doing that doesn't actually guarantee consistent throttling behavior. ASUS! Now, are you not a Threadripper user? This still applies to you. We know from all the users in the community that have reported in over the last year, most of the server memory that I have in the spec, it says 75 or 85 degrees C. Some JEDEC 4800 I've seen asks for throttling as low as 65 degrees C. Server memory, it's part of the spec. For the chips themselves, the spec is for the JEDEC configuration. So like you can look up Micron memory chips and be like, oh, this is what this is. But desktop memory configurations throw all of that out the window because of the voltage and because of the configuration and other stuff. Real world experience with desktop memory temperatures, instability can creep in all over the place. You can notice instability pretty low. On top of that, with desktop memory, what sensor are you using? Does the desktop DIMM designer even put the sensor where it's called for? Maybe they just put one. Where are you reading that from? Where are you reading the voltage regulation temperature? Can the voltage regulation stuff go to 100 degrees C? I mean, sometimes, and sometimes that's fine. Server JEDEC standard operating voltage is 1.1 volts, but Expo and XMP voltages can be as high as 1.4 volts. There's also low-level concerns about the signal-to-noise ratio, like just how the DIMM is in the socket can cause signal-to-noise changes. Thermal, whether the system is hot or cold, can change signal integrity. You might have experienced this on desktop. Sometimes your computer, when it's been off for a while, takes a long time to turn on after it's cold. The memory has to be retrained. Servers being off and memory retraining from hot to cold, is not really at the top of the spec design in JEDEC DDR5 because remember, it's server first. There is some thermal training stuff in there, but the context of that is different. See what I did there? Memory context restore. That's an incredible joke. Definitely deserves an update. So desktop platforms like AM5 and LGA 1700s, users, desktop DDR5 DIMM instability has been seen as low as 55 degrees C. That doesn't mean desktop DDR5 is rated for 55 degrees C. It just means the system was already on edge and the heat pushed it over. Adding more cooling solved those users' haunted PCs even as low, as 55 degrees C. If you're running DDR5 desktop or workstation, do this. Monitor your DIMM temperatures. How? On Windows, there's Hardware Info 64. This is an excellent program that has never let me down. We use it in a lot of our videos. On Linux, LM Sensors and RASDaemon. RASDaemon is a killer app. It should be installed and enabled by default. A lot of our Linux how-tos have that. Check your memory, touch it. Can you do something to actively cool it better? Make some changes to actively cool it better. You can go 3D print some stuff. Arctic 40mm fans and 3D printability, literally what's running in here. Ducts and shrouds, we have those too for Fractal and Silverstone cases. Watch for silent throttling. Even if your throttling is working correctly, you may be hurting performance. I did a script using Intel's memory latency checker utility to generate both an artificial load and monitor the memory bandwidth for signs of throttling. It's a great sort of 1-2 punch to do that because there wasn't something out there that really does that. DDR5 is powerful but harsh and unforgiving. Oh, and by the way, we know from our users that this can also manifest as mysterious stutters in games as you teeter between throttling and not throttling states, especially in like your 1% lows and your 0.1% lows. And if you're on Threadripper with an ASUS board, update your BIOS. I'm going to pin a comment below when we've got the updated BIOS. Maybe check out some of the other videos which are a little more in-depth and a little more technical and maybe a little too much in the weeds. Now, as you add airflow, keep an eye on those DIMM temperatures. And I'll be happy to discuss all of this further and answer your questions or whatever in the Level 1 community and at our forum, because that's what our forum is for. I was incredibly surprised by several reports of stability improvements from normal desktop users in our user community just by adding some DDR5 cooling at temperatures that I would have considered safe. Desktop is something that I do need more data on. We know Workstation has a really pretty egregious bug if you're on ASUS. So let's keep gathering data and let's get together as a community and keep an eye on this, because You got to protect your DIMMs. Your DIMMs got to be covered. Cover your DIMMs, because you don't want to buy more DIMMs. I will. This is Level 1 Techs. If you have any questions or you want to talk about it more, that's what the community's for. All right, I'm signing out, and I'll see you there.